Thanks. Yeah, keep the bag here.
All right. So today we are going to talk about sampling. Actually, we made it a projector very short. So sampling is necessary for many things. We're gonna use it next time, Wednesday, as an example for how to deal with LDA. But because sampling is not typically something that people study in their undergrad, I mean some of you do, we'll take it in baby steps, and we may not reach the point where you can implement sampling for LDA. But we'll reach the interesting point where sampling from a conditional distribution. So how that goes, let's start with the basic stuff. Create some sort of plan here. So we talk about sampling. So let's write a master plan. We have uniform versus not uniform. If it's not uniform, we need to have a sampling distribution, right? So not uniform means sampling distribution or density, sometimes called. And if we have such a distribution, we might call it PDF. Stands for what? Probability density function. We might call it P of X, something like that, right? Probability of the random variable X. We might call it F of X, as in the input function F that we want to sample from. Right? If it's uniform, we don't need a sampling distribution, because uniform means everyone is equally likely. So we have that. Then we have discrete versus continuous. What's an example of discrete sampling? The space, the space of this is the random variable, right? The space of this random variable is a finite set. For example, what's the typical example everybody sees the first time when they hear the probabilities? We have a what? Die, right? We have a roll of a die. X equal value of die roll, right? I roll the die, I see what's coming up. Where what is the space? So the space, there is a fancy Greek letter for the space of a random variable, but it's not consistent across textbooks. And it's really annoying to write. So I'm just going to call it space. That is, what are the possible values of this random variable? So the space of X in that case is what?
1 to 6.
1 to 6. Many data problems are actually discrete because we sample data, which even if I have a lot of data points, those are discrete points. What's another very typical example that people hear of when talk about probabilities? Another discrete example. Instead of rolling a die, I do what? Toss a coin. Flip a coin or toss a coin. So if X is the value of a coin toss or flip, then the space of X is what? Heads or tail. Heads or tail. Heads are typically count as 1 and tail are count as 0, right? Two values, binary and the variable. So in these discrete problems, obviously makes sense to talk about uniform versus not uniform. You should always ask yourself these questions when you say implement sampling. What's my space? What am I sampling? What are my objects? Or like coin tosses or die rolls or data or things like that, right? And then does it make sense to say my die is uniform versus not uniform? Can I have a non-uniform die?
bias.
Right. It's possible that some die either by a manufacturing defect or because somebody hacked it. In gambling, it'd be quite useful to hack a die to produce more sixes, for example, than ones, right? How about the coin? Can I talk about a coin that's not uniform? Yes, I may have a coin that has more likely than more than 50% chance to be a head, for example, right? Okay, so I can talk about that, but in here, in a continuous space, what do I mean by continuous? Discrete space of probability if is a finite set. In here, the space of my random variable is typically, I'm going to say equal, but I'm going to say typical, as in not necessarily always. It's some sort of the real axis, maybe, right, at some power d. That means to say d is the number of dimensions, and this will be the interval from minus infinity to plus infinity times minus infinity to plus infinity times plus infinity. It essentially says my random variable has so many components in it, right? So these are components. So I think we've seen this a little bit, something very related to this. When I talked about Gaussian, multi-dimensional Gaussian distributions, right? We have a density function that is on multiple variables. So the simple case, of course, is d equal 1, when I have only one variable, right? And then my f of x, it's a continuous function on R if it's a one-dimensional variable. So what's the intuition here? If I say the probability of rolling the die get a 2 is 20%. That really means intuitively, without mathematics, what? If I say you have a die has been hacked, probability of rolling the die being a 2, it's about 20%. What does that mean?
You're rolling 100 times, 20 times, you get it.
If I keep rolling it, roughly 20% of the time, I'm going to get a 2. There's another notion that we didn't discuss yet, independent versus dependent, right? So I'm gonna discrete versus continuous, that's one thing. This is one property, this is another property. I have one that's independent versus dependent. Yes. Typically, when I roll dice or flip coins, I'm assuming independence, right? Typically, people say roll the die 3 times. They mean each roll of the die is independent of the other rolls. Or flip a coin 20 times. They mean flipping the coin, it's independent of the flips you already have. But in practice, of course, many data problems have dependent sampling in them. Okay. So in the discrete, I think there's a very clear intuition. If I say the probability of getting a 2 is 20%, that means 20% of the time, 1/5 of your rolls are roughly being 2s, right? And I can measure this with a histogram, right? A histogram is what? So let's add here at the discrete, let's add this. So I sample independently, say, n equal maybe 200 times, right? I didn't say how, but let's say I have a procedure for sampling that. And I count values observed. Now these values are, of course, parts of this space of x, right? If I roll a die, I'm going to observe values 1, 2, 3, 4, 5, 6. And when I build a histogram, how does that look like, a histogram for a die? I have 1, 2, 3, 4, 5, and 6, right? Those are the values of the random variable. So values observed. And here I have what?
Frequency.
So if it's a uniform die, I expect roughly uniform counts, but maybe my die is not uniform, has more sixes, right? And maybe the other are more sixes and more fours. And the other are more like smaller values. Clearly not a uniform die if I roll it hard enough and I see big values in 4 and 6s. Now, the very interesting question in statistics that as soon as it's a little bit interesting, it's also a lot more difficult mathematically. For example, if you're a casino or if you are a player in a casino, right? If you notice something that's not as expected, this is not as expected, right? If I roll a die, I would 100, 200 times, I would expect roughly a uniform distribution. But expect doesn't mean it's guaranteed to happen, right? Is it possible to roll a fair die and obtain this distribution of counts?
Yes.
Again, is it theoretically possible to have a fair die? If I roll it 200 times, I get to see this.
No.
Certainly possible. How about, is it possible to roll a fair die 200 times and see only 6s?
It is.
Is it theoretically possible?
No.
What's the chance of rolling a fair die and seeing only 6s? So what is the probability of 200 roll of a fair die, all 6s? What is the chance for that happening? 1/6, because that's the chance of seeing a 6 at power 200. It's a pretty small number, right? But it's theoretically possible. So people have this question, which is very practical for a lot of risk assessments and a lot of hypothesis measurements. If I see this, can this come from a fair die? What's the likelihood that observing this kind of histogram comes from a fair die? Because theoretically it's possible to come from a fair die. No matter how skewed this histogram is, it's theoretically possible to come from a fair die, because a fair die can output any histogram in theory. Of course, in practice, the probability of a skewed distribution is much less likely than a histogram of a rather uniform distribution. So if you are a player or in a casino and you see somebody winning a lot, for example, on blackjack, you could ask the same question. Is this player not playing correctly, not cheating in any way? Is it possible that a player who plays correctly blackjack or roulette or 21, right, or poker, wins consistently a lot? Yes, it's possible. What's the chance of that happening? It's very small. So casinos will have mathematicians. That's a great place to work as a mathematician. They have mathematicians and models who says, if this player wins a lot, should we investigate him or not? When it gets too weird, too unlikely to happen, they start investigations. Are you having cameras? Do you have other people that help you? Because it becomes very unlikely a player that plays correctly to start winning a lot. Okay? So that's what I'm going to observe. And there are those questions which is like, what is the chance for fair die to produce this distribution? And what is the chance for this distribution to come from a fair die, which is not exactly the same question. Okay, so I can talk about discrete versus continuous. In a discrete only, I have another branch here. So I'm going to put only for discrete. I can talk about, so I'm going to say discrete only, with replacement versus without replacement. That is to say, I think we mentioned this already, if I sample something, I get the value, the replacement versus not replacement refers to whether that value is possible next time when I sample. So the die rolls are with replacement or without?
With replacement.
Certainly with replacement, because I'm not posting the problem like once you see a 5, you can't see a 5 again. How about the cost points? Definitely with replacement. So what kind of problems make sense with replacement, without replacement? I'm still in a discrete space, so my sampling is within a bunch of objects. Does it make sense for a die to sample without replacement? Is there any sort of problem you can think of where you have a die with 6 faces and you want to, this of course, all the sampling discussed here refers to more than one draw. There is the initial draw, roll the die once, toss the coin once, right? This idea of just sampling one object, it's very easy. That's probably something you have done in high school, say, you know, where you only want to pick one thing out of how many you have. All this idea discussed here refers to picking more than one thing, right? So either die rolls or data points or flip coins and so on and so forth. We want to obtain more than one sample, or the sample has to have size more than one. We're going to have this parameter n or k that refers to how big the sample we want to be. So assuming our sample is not 1, it's more than 1. Why doesn't it make sense for dice to be without replacement? Or why it does make sense? Or for coins, if somebody flips a coin and he flips it 100 times or 20 times, would it make sense to be without replacement? What would that even mean for a coin to be without replacement? When you flip it the first time, you get the value, which is either heads or tail. And then, what?
It's one problem.
The second time, you guarantee to get the other value because there's only one left. And can you even go more than 2?
No.
No. For this kind of problem, it doesn't make sense to say without replacement, right? Because what's the point of sampling without replacement a value that has only 2 possibilities, right? That only makes sense with or without replacement if the space of X is relatively large. So space of X is relatively large. So I think everybody understands that for this kind of small spaces like a die or a coin, I need to do it with replacement. And with replacement probability are rather easy. For example, for a coin, we have this probability, which I think you've seen already. What is the probability of do n flips of a fair coin and observe, say, k heads? What is the probability to pick a quarter, fair coin, presumably, flip it 200 times and observe 120 heads? Everybody knows that? It's a binomial distribution, right? So roughly, I'm going to say roughly, you'll get that in a second. What is the binomial? N choose k, yes, n big N, and choose k. What? What do I raise to k? Probability of heads. So p at k, 1 minus p, n minus k, where p is the probability of head, which is, if the coin is fair, 1 by 2. I say approximatively sometimes, meaning if I have some values that I didn't normalize yet, I may have to normalize them. And I typically say that when I don't want to think about normalization, right? So if anybody knows if I sum up those numbers for all possible k, right? If I flip a coin 200 times, what is the possible value of heads? I may have 0 heads, 1 head, 2 heads, 3 heads, 4 heads, up to maximum 200 heads. So I get 200 values, which is the probability of 1 head, probability of 2 heads, 3 heads, 4 heads, up to 200 heads. Are those now disjointed? I count everything correctly? Can a particular flip of 200 produce in the same time 3 heads and 20 heads? So when I sum up these numbers, I'm asking, am I counting correctly those probabilities? So when you count discrete count sequences, especially if you took a discrete math class, you have this question of maybe I counted a particular sequence twice. If I count all the people who are males and all the people who get A in my class, I've counted 2 people twice. In here, that's not the case, because if I run it 200 times, that sequence of 200 flips certainly has a fixed number of heads in it once I see it. Right? So if I partition the possibilities into all possibilities with 1 head, 0 heads, 1 head, 2 heads, 3 heads, that's all of them. So if I sum up these numbers by k, does it sum to 1? So if I, again, the k is the how many heads can you observe, and I do sum over k of n choose k, p at k, 1 minus p at n minus k, from k equal, what's the minimum number of heads? 0 up to n, all of them. Is that summing to 1? Yeah.
Yes.
So I could have said equal here. Sometimes when I don't want to worry about normalization, I may use proportional probabilities to the ones I need, but they don't necessarily sum to 1. So if they don't sum to 1, to get an actual density function, one would have to normalize it, right? Take all these values and divide by the total. Sounds really easy, but a lot of Bayesian estimation problems, the most difficult step is the normalization. In fact, there are algorithms that specifically don't normalize because that's a very difficult step. So sometimes we're going to put this sign approximative and say that's proportional with that, but the probability is not necessarily sum to 1. Okay, so far so good. Does it make sense in a continuous space to talk about replacement versus not replacement? So in a continuous space, what is some example of continuous examples, right? Can do uniform. Is that an example of continuous distribution? So uniform in an interval, say from 0 to 1, right? That means every value outside this interval, it's impossible, but every value in this interval is equally likely. Okay. I could do Gaussian, right? Say. Gaussian will have some mean and some parameter, let's say sigma matrix, right? So the uniform, if we were to plot it, look like from 0 to 1, right? This is 0, this is 1. There is some particular density function here. This is f, and then it drops down. It's nothing. On the outside 0 or 1, there's nothing. Gaussian, of course, if you plot it, you get some nice bell with the mean and variance. So what I want to talk about now is what makes sense and what doesn't make sense. And how does these densities relate to the histograms? Histograms is you plot what you sample. Histograms can be done for continuous and non-continuous distributions, right? I can roll the die and observe some values and count to see what values I've got. And I could also sample from a Gaussian distribution and see what values I've got. Except I need to do something for a histogram if I sample from Gaussian distributions or continuous distributions. What should I do? Bucket it, right? It doesn't make sense to count exact values that are obtained because I can't obtain exactly the same value twice. Real numbers are too many to think that if you sample 200 times, you're going to get exactly the same value twice. That's why this notion here, replacement without replacement, doesn't directly apply to continuous distributions. If you sample a finite sample from a Gaussian distribution, you're not going to get the same exact value twice. But with die rolls, you're guaranteed to get the same exact value twice because the values are only 1 to 6. So in a continuous space, if I want a histogram, probably do buckets. So I can bucket the space of my random variable, say from 0 to 0.1, here's another space, another space, another space. And I can still count how many values I've got in each bucket, and the bar will indicate how many values are there, right? Good. If I use buckets as my notion of replacement or not replacement, of course, I typically sample with replacement, right? Because when I sample from a Gaussian distribution and I bucket it, I could get multiple values in the same bucket. Now, what about this? When is this a thing? So again, technically, if we sample from a continuous distribution without bucketing, there's no notion of replacement because the exact values produced cannot be the same. The chance of two sample values from any uniform distribution to be exactly the same, that's impossible. It's only possible if your program truncates by a bunch of decimals and then they happen to have the same truncation, but theoretically it's not possible to get the same value. But bucketing certainly is possible, right? If this is a 10% of the distribution, and so I already have a value here, the chance of the next value coming here is 10%, so that works out. When would I use this? So I'm back to the discrete case. I sampled, and we said earlier, if you roll a die, it probably doesn't make sense to roll it without replacement, because what kind of problem says roll the die, you get a 3, and then roll it next, 3 is not allowed anymore. And you see a 5, now 3 and 5 are not allowed anymore. Doesn't make sense, I think, for a lot of problem involving dice, right? But when does it? So when do I need to sample without replacement? What kind of problem is that? I have a discrete space. Why do I want to sample without replacement? Can you give me an example? And what do I sample?
You pick several cards.
I sample the cards from the deck, 52 cards. Okay.
Yeah, the probability of the.
So I agree that sampling it from a deck of cards, you probably don't want to sample the same card twice, right? But I don't think sampling from a deck of cards. Why is that necessary for poker, sampling from a deck of cards? Who would need such a problem?
Could you repeat that? Could you?
So you're saying if you want to sample a poker hand, how many cards are in poker when you get 5 cards, right? He's saying if you want to sample presumably 5 cards, you want to sample them without replacement. Because once you pick a card, the ace of spades, you can't have in the same hand another ace of spades. Is that what you're thinking, right? That makes sense because the deck of cards have only one ace of spades, so I don't want to sample it twice. But why would I need to sample a poker hand? What's the point of that?
Because you're choosing something. So if you're choosing something, you normally choose without replacement.
Right, but why would I want to choose something?
Exactly.
Huh?
Sample.
Yeah, but why? Why would I want to do that in poker?
You want to count the cards? You want to count the cards?
Count the cards in my hand?
You know, like, decide whether you want to go.
So presumably there are many possibilities for poker hands. In fact, we know how many. How many different set of 5 cards can I have? 15 choose 5, right? And I may have some sort of algorithm that plays poker or that evaluates poker or that do reinforcement learning to see what kind of decisions should you make with those hands based on whatever the poker rule games go. It will have so many possibilities to deal with. In fact, the poker player could have any one of these possibilities, right? Is it a uniform distribution here? When you get the poker hand, is it equally likely to have any combination of the 5 cards?
Yes.
Right, so that's uniform, right? So now if I have some method that estimates, for example, gain or losses or what to do next, like a machine learning algorithm, why would I need to sample? Why can't you just figure out what I do for any one of those things?
There will be other players who will be choosing something.
Yeah.
So,
But why sample and not consider every single possibility of them? There's too many, right?
Yeah.
So if I want to make an estimation of things, that's a lot of what the sampling goes to, right? We want to estimate something like, say, the average gain or loss or how to play. We can't deal with every single possibility because there are too many. So then by sampling and computing some sort of average over the game, I say that average is maybe the average of the entire set of possibilities. This happens a lot. And it happened before people invented mathematics, right? People did this kind of things even 3,000 years ago without calling sampling mathematics. So more typical examples are voting polls, right? When people do voting polls, they call a bunch of randomly chosen people and say, who are you going to vote for? People say, I'm going to vote with this or with that, right? And then out of, say, 1,000 poll sample, they conclude, we believe this candidate is going to get that. The sample is a lot smaller than the entire voting population. In the United States, the voting population is about 150 million, I think. But the polls use samples of 2,000 to 3,000 people. How can they do that? How can they ask randomly 3,000 people, estimate some sort of statistics, for example, what's the average voting preference or media or something like that, and decide with so much probability this candidate is going to win? Right? It has to do with what we call sampling power. I don't need to look at all possibilities to compute or sample or estimate an average. In some cases, I need to estimate far more complex things than, say, the average or the expected value. And that's what we're going to need to do for, say, LDA. If we have to implement LDA, we're going to need to estimate the marginal of a joint distribution without having access to the joint explicitly.
How do we know like how many samples we need to generate? Estimates?
So a lot of statistics relates to the statistics is organized this way. So first we have sample, and we don't know much about sampling, so we have to start with the basics, right? Even how do you sample? That's the basic question. But then we have estimators. So that is based on a sample, I want to compute the average of my random variable. Or what else I can compute? I can compute the variance of my random variable. Now this is estimated variance. It's not a true variance necessarily. It's what I get from my sample. The next step is something called confidence intervals. Some of you may have heard this as p-values. Hypothesis testing, right? And these confidence intervals sometimes depends on the sample size, right? So these depend on the actual distribution, maybe the sampling method, definitely about the sampling size. What do we expect in terms of confidence is saying, I'm using plain English now, if I want to estimate the average, I obtain an average estimator for my sample, and then that I have to say how sure I am that that's the actual value or close to the actual value, right? So the confidence interval will relate to when I say, typically the way we see this, we have a predicted, say, E of x or mu, and it's here. And what you see a lot in a lot of academic papers is a bar that's like this. What is it saying? This is the value estimated, and the bar refers to what? Where I believe this value can be with some given probability. So this is a probability of the true expected value of x within 95%. So what I'm saying, so this is the predicted. It's here, and I'm saying with 95% chance, the true value of this average, not the one I estimate, is between here and here. So you're going to see a lot of those bars in all kinds of papers that says, I predict the value. What does it mean to be very sure in terms of these bars? When I'm very sure means bars will be small. When I'm not sure, bars will be big. So I think it's pretty clear that this sureness or confidence will depend on sampling size. Meaning the more stuff I sample, the bigger the sampling size is, the more confident I'm going to be in my estimate. And the smaller the sample size, the bigger the bars. And there are formulas for all of this stuff. All right. So back to this problem. Where do I want to sample without replacement? I want to sample a poker hand, right? A bunch of cards. This is not difficult if the sampling is uniform. We say for the poker cards that typically when somebody says draw a poker hand, you want to draw it without replacement, that's 5 cards. And typically that's uniform, right? How would you do this? Implement without replacement, draw 5 cards out of deck of 52. How do you do it? Very simple algorithm. If I tell you right now, write a program that draws 5 items out of a collection of 52 without replacement, what's your plan for such an algorithm? You draw one at random, and then remove it. Draw another one at random, remove it. Draw another one at random. Draw one at random, is that a hard thing to do? So that's our first algorithm. How do we draw one thing? So draw one item or sample randomly. But I'm going to say here from distribution f of x. X is discrete here. So I have a die and f of x are the probabilities over the faces, right? So in the die case, f is a table of, say, probability of seeing 1, probability of 2, probability 3, probability 4, probability 5, and probability 6. That's my f function, this is 6 numbers. How do I draw one at random? Again, not uniformly. Uniformly, perhaps it's very easy. Just pick one at random from the collection. You use a random number generator, do the multiply with n, take the rounding value, and maybe that's the option, right? You ready to follow me? If I want one at random between 1 and 20, I generate a random number with the random generator with 0, 1. I multiply with 20, right, to now have values between 0 and 20. I take the rounding function to get an integer, and whatever I've got, that's my sample, object number 17. But what if the probabilities are not uniform?
How we divide like the number like from 0 to 1 into different brackets?
Very good. So here's the 0, 1, right? Then we say that is P1 here, right? That's probability of 1. P2 may be very small. P3 very small. P4 very small. P5 very big. And P6 very small. So I pick something that's not uniform. And they sum to 1, right? So this is 0, this is 1. And then
Pick a number.
pick a number. So R is a random number. I use the computer random generator function. This is uniform, right? When I say random for a computer, it tries to make it uniform. Can it make it uniform, really? Pseudo number generators, can they be theoretically uniform? No.
If it is maybe that high hardware.
They cannot be uniform. They get very close to uniform, but they cannot produce uniform values because they have to have some mechanism based on what they predict functions, and this cannot be randomly uniform, right? But it's approximately uniform. And this is a number between 0 and 1, right? So here's my R value. So if the value comes there, what am I going to do? I'll put a 4, right? If it comes here, it's a 1, here's a 2, 3, 4, 5, and 6, right? So output, say t equal the interval pt where r false. Essentially, I take the f, right? Well, that sounds good, but how do you actually do it? What kind of things you write in your program? How do you do this? I mean, it looks nice schematically on the board as a drawing. Computers don't go by drawings, right? So how do you do it? Okay. So I need what? What is this? What I just drew here has a name. It's a name which is called CDF, as opposed to PDF, right? What is CDF? Cumulative density function. So how does this go? CDF of some value x, which is 3, right? Say x is 3. What is that? It's the sum of all the probabilities up to that point, right? That's the notion of CDF of 3 is the sum of P1 and P2 and P3, right? So cumulative because it's up to that point. Nice. So let's suppose I build this CDF. Would that be a linear time operation to create a CDF?
Yes.
Right. And then when R comes along, I generate an R. I do what? How do I find where R is? I put it here on the graphics, but computers can do that, can place an R on the line. So how do I know which value R falls in?
You check the CDFs and see which range it
Right.
falls.
So how do we find this output D by what kind of mechanism? Can we use binary search on the CDF? Right, because the CDF will always increase, right? So CDF is a monotonically increasing function. In other words, for every value bigger, I get bigger CDF. So because the values are sorted, I can use binary search to sort to find that value. Okay? So that's, I think, fine for width replacement. So that is draw 1. When I say draw 1, it matter replacement or no replacement because it's just 1. The replacement and replacement are important for the second draw, right? If I draw another sample, what do I do? So assuming I have a mechanism like this, I can use this very easily for width replacement, right? I draw a sample, change nothing, draw another sample, change nothing, draw another sample. That is a independent process, right? Because now my samples, since I didn't change anything, they'll be independent. What if I want a replacement without replacement?
You change the.
Can I do that? Draw value, then what?
You change the function, right?
I can't output that value again. So suppose I draw cards from a deck, or I draw students from a set of 100, right? And I don't want to speak the same student again. Or I'm this voting pollster who's calling people. I don't want to call the same person twice, right? So can I use this as a subroutine? I need to change something in it, right? Because this is definitely possible to sample the same object again. So what can I do?
probability densities have to change.
Hmm?
The probabilities have to change because
So one naive thing is to say, if you pick P4 the first time, take P4 out, and then renormalize these values. Again, if you have this option with sample with proportional probabilities that I talked about earlier, you can just let the values as they are, assuming your algorithm works with proportional values, right? Because if they're normalized or not, it's still going to work. It's going to pick something proportional, the value remains. So that's a very naive thing that I've implemented on my computer, and I'm going to show it to you. But what's the problem with it? In general, what's the problem without replacement sampling? If I tell you n is 1, it's going to come out exactly with these probabilities, right? The first time I roll the die, in my case here, I'm going to get the probability of a 4. It's exactly what was the specification of probability of a 4, right? But if I sample without replacement a lot, what's going to happen in the die if I sample 6 times? What's going to be my output if I sample 6 times from a die without replacement?
half an hour.
All faces, right? Independent of the sampling probability, right? That's the same thing that's going to happen with data or the students. If I have a bunch of students and I sample without replacement, and I design a sampling distribution that's very skewed, the truth is if I sample all the students, at the very end, I'm going to have a sample with all students. So my point here is that when you sample without replacement, independent of the probabilities you have, the sampling distribution must change. By the time you reach to the last student, there's only one option with 100% chance to pick that last student. So okay, somebody could say, yeah, but we're never going to sample. If you're a pollster and you call people on the phone to ask them who you're going to vote for, are we going to really reach the sample to be 150 million? No. So sampling with replacement doesn't refer to this problem of, okay, what happens when you sample everybody? You sample everybody, you're going to get everybody. But let's the reason this doesn't work for a die is because there's no problem with dies that require sampling without replacement, like we already said. But let's take the pollster example. I'm a pollster. I sample. It's not the case that I'm going to sample everybody. I don't plan to make 150 million phone calls. But I'm going to sample 3,000 people or 5,000 people. Right? It's very small sample. The probabilities are 2 kinds of probabilities here. That is my main point in what I'm saying. There is the original probabilities, presumably not uniform. And then as I sample, the probabilities must change if I sample without replacement. To see this without mathematics, take the case when you sample all the way to sample everybody. At that point, you're forced to get everybody. So how can I implement sampling without replacement that kind of agree with the probability distribution if I'm forced to change the sampling distribution with every sample I draw? This has been a problem in statistics for many, many years, and it still is. And there's 2 kinds of distributions. The one that I start with, so that's my distribution over faces, and the one that I end up with. So in a die case, if I sample 3 things, three faces out of 6, I'm going to have a certain probability for each face that we call the posterior probability. That is, what is the chance that my face got sampled, my number 3. So I don't want to put math on the board, but I want to emphasize this point, that the sampling distribution that I start with, imagine these values. Maybe this is a small, 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 and those 2 are big. So let's say these are 1/3, 1/3, right? And together they account for 2/3. And I have 1/3 left to divide by 4, so maybe that's 1/12. If I ask you sample 3 objects from this distribution without replacement, what is going to be the probability of seeing a 1 in the sample? If I draw only one object, not 3, so I say here n equal 3. If I draw only one object, what's the probability of seeing the 1? 1/3. But then what you guys said, after the first sample, whoever got sampled get kicked out, the values gets renormalized, and then I sample a second time, right? What's the probability the second time to see a 1?
0.
Huh? If I see the first time a 1, it's 0. But if I haven't seen the first time a 1, now what's my chance in the second round? Probabilities have changed now. Right? And if I haven't seen a 1 the first time and the second time, what's the chance to see the third time? Because I'm sampling 3 things, right? It gets very messy very fast, these things. And my point for right now is that the ultimate actual inclusion probabilities, right? What's the probability? This is called an inclusion probabilities. Inclusion probability, which is a post sample. So this is computed after I'm done with the sampling algorithm. So this is asking, do whatever you want to do, sampling without replacement. At the very end, what is the overall chance for 1 to be in the sample? There's a chance, right? Whatever mechanism gets implemented, there's a certain chance that 1 gets included, and 1 minus that is that the 1 is not included. This is an extremely useful probability. In fact, many estimators, many statistics designed for calculating all kinds of things rely only on this inclusion probability. They don't need to know how the sample was obtained. What people ask to compute statistics, they're like, you have to give me at the end of your algorithm, you can do whatever you want, but at the end, you have to give me the probability for every object being included in the sample. But that has to be the correct probability. And the difficulty is it's hard. For any schema that you guys came up with the most obvious one, take the object out and renormalize the probabilities. Even for this one, after k samples, how did the probabilities change? Computing this overall inclusion probabilities is not practical further than k equal 2. So if you do 200 samples, that's completely impossible. Am I making my point clear enough?
Yeah.
In many without replacement schemas, the schema itself doesn't matter as long as at the very, very end you could say, for here's all my data points, what was the chance that every data point or every person or every email was included in my sample? This is trivial for uniform sampling. Why?
The probability don't change.
Wait a minute. If I say my sample size, my space is 1,000,000 things, and I sample with the uniform probabilities 1,000 of them. Okay? It's all uniform. What's the chance that one person out of this 1,000,000 gets selected? Again, I do uniformly. I have 1,000,000 people to call for election. I don't call all of them. I choose a sample of only 1,000 of them. What is the chance that one person gets included in my sample to actually give him a phone call, ask him who you vote for? What? Why? It's actually 1,000 out of 1,000,000. So what's 1,000? This is the n, the sample size. And what is this? This is the space of X set, right? So in a uniform case, that's very easy. Assuming the algorithm really did it uniformly. I don't have to actually compute anything. I can only go by, if you're really asking 1,000 people out of 1,000,000 and you want to be random, the chance of somebody being included is that versus that. What happens if I want to sample 500,000 people? What would be out of 1,000,000 voting population? What's my chance for any person to be included? 1/2, right? Because 500,000 out of 1,000,000, so everybody gets a uniform chance of 1/2. This is extremely difficult problem if the probability is not uniform. In fact, people have thought of this and said, hey, it probably doesn't make much sense to think about it this way as a sampling given probability. It's much better to think, implement a sampling method, but have a target sampling distribution. So think of this not as a distribution I'm drawing from samples, which could be people or email or patients or students, but think of it as the final inclusion probability target. So I can draw some mechanism, and my point would be that the inclusion probabilities overall to be that. Also very hard problem. So there are quite a few methods that approximate this idea. How can I get there? So I'm gonna connect my computer here and talk a little bit about this as a visualization. This is part of an undergraduate class. To instantiate all this with some samples here. So I have here a piece of MATLAB code that does some sampling, various a few cases, few basic coins and roll dice and stuff like that. So essentially, I'm going to ask for one of these things, one Ryle-Dold uniform, and this is setting up the problem. It says D is 1, that's one die, and n equals 6 because this n is not the n I have on the board. This n is the space, right? So 6 faces. The probabilities are uniform, right? That's what it says here. And then once this setup is done, there is a procedure that's being called with replacement or without replacement that does the sampling. So how this stuff looks like. Suppose I'm going to do, I want to roll the die 10 times. I don't know if you can see this. Too small. So I roll the die 10 times. That's not working without replacement. I can't roll a die 10 times without replacement. Why? There's only 6 things to pick from, right? Let's try this one. So what this is doing is saying, okay, if this is the count you got. When you roll the die 10 times, you got how many ones?
3.
1 2s, 3, so 2 3s, so on and so forth, right? And what this program allows me is to roll it again. I can press enter here, and I keep rolling it. And if I do it multiple times, those bars are like the totals corresponding now to a sample size of size 80, because every time I press the button, I sample 10 rolls, right? And the green ones is the last roll. What happened in the last roll? Last 10. And this red bar here is the estimated average. What is the theoretical average of a uniform die? The expected value. Do we know, everybody knows the expected value formula? Yeah. Expected value of x is the sum over all possibilities into the space of x, right? Of the value times probability. So for a die, uniform die is the simple average. Uniform means simple average. So the average of the values is 3.5. So my red bar is not at 3.5 because this is computed from the sample. I take the sample values and I average them. I'm not necessarily getting a 3.5. But what should happen here? The more I sample, the more this average should get to closer to 3.5. Does it? Close enough. Right? So this is sample size of 1900 samples. Okay. I also have standard deviation, also computed from the sample, right? As opposed to the true standard deviation, which there is a mathematical formula for it. There is a way to measure standard deviation if you want to have an unbiased estimate. You divide by n minus 1. Do we know that? Instead of divide by n, we divide by n minus 1. That is the difference between the value and the mean squared. Take an average of those values. That would be variance, but to be unbiased, divide by n minus 1. Okay. So I have this sample. Let's try something else. Let's try, what else do we have here? So how about this non-uniform? Suppose I want to do this, get a new figure. Now that's not uniform, it's, it has some probabilities that are predefined there. So when I sample this, I look at my probabilities, what do I see? 0.3, 0.1, 0.1, 0.1, 0.1, 0.1, 0.3. What are the big probabilities? Or 1 and 6, right? So if I sample from this distribution, I'm going to see more 1 and 6s, right? Because the sampling probabilities for 1 and 6 are bigger. But what happened to the average? The average is still 3.5. It turns out this distribution is symmetric on the left, small side versus big side. So that's a way to tell you, if you look at the average, you're not going to know if the die is fake or not. Because you could have an average that corresponds to the same. So let me try some other things that we have here. How about this? I'm rolling now 2 dice. So what I'm printing there is the sum of the 2 values. So I'm rolling 2 dice and I sum up the values, right? I'm not plotting each pair, because when I roll 2 dice, I get 2 values, right? What I'm plotting here is the sum of the 2 values. So the minimum sum when you roll 2 dice is 2, right? And the maximum is 12. And why do I get something like that, bumpy? I don't want to say central limit theorem. I don't even think that's the reason. Much more down-to-earth reason. Why is it that overall I get more 7s, 6s, and 8s than 2s and 12s?
There are more possibilities of getting a 7.
When I roll 2 dice, how can I get a 7? 3 and 4, 2 and 5, 1 and 6, so on and so forth, right? And how can I get a 2? Only 1 plus 1, or 6 plus 6. So just the fact that when I roll a die, the chance of a 7 is maybe 5 combinations out of how many possible, how many combinations will I roll 2 dice? What's the space now? It's 36 possibilities, right? Because I have 1, 1, 2, 1, 3, 1, 4, up to like 5, 6, 6, 1, 6, 2, 6, 3, right? So 36 possibilities. This and every roll, it's more likely than the other one. So when you start adding them up, you get the bigger body. And what's my average for all this when I roll a die, 2 dice, and I take the average? That would be around 7, right? Because if you look at all 36 possibilities, the average is 7, and my estimated value is pretty close to the average here. How about the coins? If I start flipping coins, I have here other examples, but let's look at coins first, if we can find them. coin toss fair. Let's throw one that's not fair. So the one that's not fair has a probability of 30% versus 70% here. So if I do that instead, 0, 1 here are the heads and the tails. And this tells me how many heads versus how many tails I've got. This should match the binomial distribution, right? If I sample enough, the how many heads I have versus how many tails I have for a coin. I have other examples. I think I'm going to show you one more. Here's 1,000 car prices. Let's do this one. Car prices. This is doing it with replacement, I think. That's how I call it, with replacement. So that's 10, sampling 10. And now suppose I sample a bunch of those. I get this, which is going to have to start, this is a histogram, like we said earlier, histogram. It's going to have to start looking as the distribution from which I sample, right? So the distribution for which I sample here is a normal distribution. So I sample from a Bell distribution that has a certain mean and variance, right? So I'm gonna get, if those are car prices, the average is around where the mean is, and there's like normal distribution says the density gets concentrated around the mean, and the falling out is quadratic exponential. It's an exponential in x squared, right? So is this looking at as a Gaussian? Maybe not. Maybe I need to do more samples. It may take a lot of samples until this looks exactly like a Gaussian. But what I'm doing here really, I'm going to have to delve into the algorithm of how this actually happens. The Gaussian distribution, is it discrete or continuous? Continuous. So how did this happen? Turns out my program is cheating here. Right? I'm not really implementing sampling from a Gaussian distribution. What I'm doing, I'm asking MATLAB to sample a bunch of things from a Gaussian distribution. And then in my program here, when I say with replacement, this is the naive with replacement that says for so many iterations, sample one and move on, don't change anything. And if I sample without replacement, I'm renormalizing the probability by keeping track of who's available. So every time something is not available, it's not counted in my probability space. But the reason this works is that I'm essentially doing a uniform sampling over a set that has been sampled by MATLAB according to the normal distribution. So MATLAB here did the heavy lifting by giving me this set of normally distributed values through which am I sampling uniform. So many sampling procedure will have this kind of phenomena. Use something to do some part. I'm using MATLAB here to do the sampling. When I call the normal distribution, it's going to give me a set of 6,000 or 8,000 values sampling from a normal distribution. And then I'm saying uniformly, if you want only 20, sample 20 of those that already have been sampled from normal distribution. Is that a valid procedure? I mean, not the fact that MATLAB does the heavy lifting. I could have asked MATLAB to give me just 20. Is it valid to say, sample with MATLAB with a normal distribution 6,000 objects or 60,000 objects, and then uniformly take 100 out of those if you want 100? Would that be a valid sample of 100 from normal distribution?
is you're picking up 100 from the 2000 or whatever you picked up from the distribution. So you're essentially limiting your, you're giving more bias to those 2000 values in your sampling.
I'm not sure. So do you guys understand my question here? I got MATLAB to say, give me, I don't know, I think 6,000 objects from a normal distribution. Let's assume MATLAB does the correct job. It really samples 6,000 things without replacement from a normal distribution. Fine. Actually, as I said, without replacement doesn't make much sense on a continuous distribution because you can't get the same value twice. 6,000 values, Gaussian. And then I say, randomly, uniformly, pick 200. So I really pick 200 at random from this set. Is this a valid 200 sample as if I ask MATLAB to give me 200 from a normal distribution? That's my question. It's not an easy question. Okay.
No.
So a lot of sampling methods have this flavor. What can you do uniformly and how that combines to some other methodology that the sample starts looking correct. And they have math backends proves that if you do this uniformly through that backend procedure, your sample is going to be a valid sample. We're not going to answer that question right here today, but that's a question I'm posing to you guys because the normal distribution is quite easy. So assuming the original MATLAB sample of 6,000 things is a correct 6,000 things sample, and I sample uniformly 200 objects in it, is now that a 200 valid normal distribution sample. So let me talk a little bit about how this works in a more discrete space. If you're interested in this subject for discrete, which as data scientists, you're going to have to sample much more from discrete spaces, even big ones, than from continuous spaces. A lot of the statistics, and if you take a class in math, have to deal with PDF that are continuous distributions. But in data science, we have to sample a lot between images or people or patients. So I want to show you something that I had to do for my PhD thesis. It took me quite a while to figure out. Out of all the sampling books I've read, unfortunately the one that I found most useful is one that's very badly written. Like it's not written in a typical math form. So what this book here does, I'm not saying you should read it, I'm saying you an example of what people have studied over many, many years. This is saying I'm going to present 50 sampling methods to deal with the problem of how do you do sampling from a discrete space without replacement. Since that's an impractical problem, here's 50 methods to approximate that thing. I'm not going to talk about all 50, of course. I'm going to pick one. So let me see where that goes. I had to scan this book because this book is not available otherwise, so I got it from a friend and scanned it. So there's a theory, a bunch of theory. And then see, I think chapter 3 here, unequal probability procedures. Of course, the uniform case is very easy. If I were to draw things uniformly, that would be easy. But if I have a like a p distribution on the board that I have to draw from, what do I do? So there's a bunch of methods. I'm going to make this. I know you can't see it. It's all the theory, so I'm missing something. scan is incomplete. Sorry about that. I'll have to show it to you in a picture format. I wanted to point out of how many, I think this scan, but I'm going to show you next time. So this scan is just the theory, but it misses the actual 50 procedures. All the 50 procedure approximation to the following thing. This is one of the 50 procedures that ends up being a little bit more practical than the others. Here's the problem. We want to sample without replacement from a distribution. And I'm having a very nice distribution over there. Typically sort the items by their probability. So this procedure that's more practical in practice, what happens with this, a lot of procedures are applicable only for small sample sizes, when you want 2, 3, or 5, but for us data scientists, we usually want 100 or 200 things, and then very few procedures apply to large samples. Step number 1, bucket that distribution into the buckets equal with the sample size. So in this example, I already know I want to pick 14 items, and each bucket will be 14 things. Make sense? Now, in each bucket, I renormalize the distribution uniform per bucket. So I took all the probabilities that fit in this bucket, and I sum them up, and I make them uniform in the bucket. Step number 3, sample with replacement the buckets. So pick 14 out of these buckets with replacement, right? So it so happens maybe that this one will pick 7 times, 4 times, 2 times, so on and so forth. This is the counter bucket. And then figure out what to do. But I want to recap the first 3 steps. What is my task here? Sample from that distribution 14 items without replacement. This is an intractable problem to do it exact. So all methods are approximations of it. I'm going to show you one. Take the 14 items and say, the sample size I want is 14, but the number of objects could be 1,000,000, right? The first 14, the next 14, the next 14, next 14, so on and so forth, sorted by the probability. Those are my buckets. Inside each bucket, I sum up the probabilities, divide by 14, and everybody gets a uniform probability. So I replace the actual probability of an item with the probability inside the bucket, which is uniform in the bucket. Now the buckets have mass. This probability still sum to 1. If those probabilities were summing to 1, these still sum to 1. Why? In each bucket, the sum is the same. Because I took the sum divided by how many they are, right? So they still sum to 1. So now I think of this whole thing as a probability of a bucket. The chunk in the bucket. I sampled the buckets based on now how many buckets I have. 1,000,000 divided by 14, right? Because each bucket has 14 items. I have so many buckets. I sampled them with replacement 14 times. Can I do that using this procedure over here with replacement? Sample a bucket. I count, okay, maybe this one is the first sample, I count 1, but then sample with replacement, which means I don't have to change my distribution over the bucket. Sample again, so I sample it 14 times, I get a bunch of counts, some of them may be 0, if I don't happen to get that. Now, what's the maximum count on a bucket? If all the samples are in that bucket, I may have a 14 here. Then what do? I look at the items, the count I got for this bucket, and select without replacement, but uniformly, that many objects in this bucket. So this bucket has 14 objects. Every bucket has 14 objects. It got the count of 7 from the initial sampling stage of with replacement. And I say, okay, now without replacement, pick 7 out of how many are here uniformly. Can I do that easily? Without replacement, why it's easy in this case? Because it's uniform. And then here's my items actually picked. The black one, it says you want to pick 7 in here, you pick those 7. Why there is no black line here?
It's 0.
It's got a 0, right? This sounds easy enough to implement, right? It's a pretty practical procedure. It gives you the exact sampling size you wanted. That my sampling desired size was 14. Am I getting exactly 14 items here? Yes. The problem is with probabilities. What is the probability to pick this item versus that item versus that item? Do they correspond? What's the correspondence between the properties I get, inclusion probabilities, overall chance of picking items, and the original probabilities? It's not hard to compute the probabilities that I get, right? What's the probability of selecting an item here? In the second stage, is count divided by how many items are in there, right? Because we said in a uniform, without replacement sampling, if you want 4 out of 14 uniformly, the chance to be selected is 4 out of 14. The problem is, what is this 4? How? What's the count? Where's the count coming from? That's in the first stage. And what's the chance of being a 4? It's a little bit like with the coins, right? Every one of these bucket has some fixed probability, and I did it with replacement. So what's the chance for this one being selected exactly 4 times? It's like a multinomial distribution over there. For coin, it's two faces, so it's a binomial. It's multinomial because there are multiple of those, right? So then I'll have to evaluate mathematically to say, what's the distribution I actually get on these items, the sampling inclusion probabilities, what's the chance to include that, versus what was the original sampling probability that was given to me. You can see that these cannot match those because those 14 items will have exactly the same probability. And they didn't have the same exact probability originally. But this bucket is very small compared to the size. So the fact that these 14 items have all the same probability probably corresponds to some items that are close enough anyway. So it's an approximation. I get the sample size exact, 14, but I sacrifice the probabilities. The actual probabilities to be sampled from are not the original, are just an approximation. Of course, a book will have a lot of equations and will prove that these probabilities are close enough to the original probabilities. All methods for doing this are approximations. How about a method that preserves probabilities but doesn't necessarily track the sample size? Say I want 14 things, but I don't get 14. Instead, I get more accurate probabilities. Riku mentioned this before. If I sample objects independently, I ignore the set. I just pick one document. I say, what's the probability of sample this object? 0.05. Sample it exactly with probability 0.05. Now the sampling probability, the inclusion in the sample, it's exactly the probability was given to me. But this method cannot guarantee a sample size, right? If I sample objects individually one by one, I can match their sampling probabilities exact, but I can't tell you how big the sample is going to be in the end, right? Suppose I sample students here with a fixed probability. I sample her with probability, 10%, 5%, 20%, I sample everybody. I can't say what's the output of this algorithm will be, how many students are going to be selected, right? If I run this procedure 3 times, I'm going to get different sample sizes. So my point is we can balance either more exact probabilities or get a more exact sample size, but they can do both. And this book that I'm going to give you guys a link is a way to say, here's approximation methods if you really want to do this. So that's what I have to say about discrete sampling, and we're going to have more ideas and more exact, like if I ask you, the homework would include some simple exercises in sampling, and there'll be more pointers of how to go by doing that. The other thing that I want to talk about a little bit, that's what we're going to continue on Wednesday. Is how to do this. So we talked more about discrete, right? This whole thing was on the board was, I have a bunch of objects. They could be many, but it's a discrete space. How about in the continuous space? We don't have too much the problem replacement versus not replacement. But how do you sample? So the basic, of course, is uniform. Continuous. And you say 0, 1. How would you do this? I say n equal 100. Again, in continuous, we don't distinguish replacement or replacement. Again, it's impossible to get the same value twice. Exact. How would you get 100 values uniformly in a 0, 1? Very easy, right? Assuming we have a random number generator, how do we do it? For p equal 1, 2, n, right? R equal random function, assuming this is 0, 1, and print this out, right? Generating a random number in 0, 1, you know, output R, outputting 100 values randomly generated 0, 1. Good. What happens if it's not uniform? I give you a function f of x, where f is defined on 0, 1 with probabilities. They have to be 0, 1, right? And instead of summing the properties to 1 are in a continuous space, how do we say this is a density function? You can say sum equal 1. We do what? Integrate. So integral from 0 to 1. Because now if we look at this function, it may be some thing. And the integral, this is the x, the space of x, right? From 0 to 1. And this is the magnitude f of a value. This integral, visually speaking, corresponds to what in this plot? And what's the CDF? So this is the PDF. What is the CDF of this function? Like before we say the sum of all the values up to that point. In here we do what?
The sum of
Integral of all the values from 0 up to that point. Right? That's the CDF. Of course, that's going to be monotonely increasing, because if it goes a little bit further, it adds more probability to it, integrates more probability. How would you sample from this distribution? Assuming you have a random number generator. This is a very easy question. I know I posed it like, wow, what a big deal. At the end of the class, it's supposed to be the climate. No, trivial. How would you do it? Imagine, in the interest of time, imagine yourself throwing a darts at the board. And you bound in the 0, 1. You throw darts here. You know the darts game? Throw something at that. Suppose you throw darts, it's uniform in this rectangle. So it can go outside, but inside this rectangle is uniform. And we know how to throw darts uniform because we know how to sample uniformly. Except not in a 1D, we sample now in 2D. So we throw darts in this rectangle. And how do I get a sample like that to work for my function? If my darts come here, I do what? Right here. So the darts could come here or here. And sampling, the output of a sampling procedure is the X space, right? Right? When we sample, we produce values in the space of X. If we sample, if we roll the die, we produce what? 1, 2, 3, 4, 5 with counts. In here, we're also going to produce values with counts. I mean, counts are 1 because we can't repeat the same value, but we're going to produce a discrete sample of only 100 things, right? So if I throw 100 darts inside my darts, 100 is not a good number because I want 100. But I throw a bunch of darts, 300 maybe. How do I sample now? I want, obviously, if I consider all my darts and I took their X value, that's going to be uniform, right? If I look at the uniform darts in this rectangle and I took the X values of these darts, isn't going to be a uniform between 0 and 1. Every dart has a uniform chance of being between 0 and 1 and a uniform chance to being between 0 and 1 here, right? So if I look at all the X values, they're going to be uniformly distributed. Right? Uniform times uniform, if we marginalize it, we get a uniform distribution. But what should I do to get X values according to F distribution? Only consider some of these darts, some of these hitting points. Which ones? Right. So why is it that if I ignore the darts that are outside, all this I ignore, and I'm only considering the ones under f of x, why is it that now the chance of picking a particular x value is not uniform? It's corresponding to f around there. What's the intuition? In here, I'm not going to have a high chance of producing this value because looking at f is small, so a lot of my darts in this area will be above f. But in here, I'm going to have more points that are in this area because the f is high enough, so there will be a higher chance to picking something here than in here. These methods, you work for any f if you can compute f, right? So what would it take? Sample uniformly in 0, 1 times 0, 1. And only, this is a pair AB, right, two values. Only keep the ones that have B smaller than f of A, right? Because this is A, this is B. So output now the A's. If it's smaller than F. Everybody follows this intuition? If I sample blanket this rectangle with point sample, but I only keep the ones under F, I get a sample that's according to F now. This is a well-known sampling method. It's called acceptance rejection sampling. Some people call it just rejection sampling. Rejecting or rejected sampling. So that is not an impractical algorithm. It's something that people can actually use, right? Assuming for every x, for every a we get, we can compute f of x. Because we need to know if the value sample b, the other coordinate, is smaller or not than f of a. So we need to compute f of a, which usually we do, right? We can, usually. If it's a unidimensional variable, we have to be able to compute f of a. We can get a sample now that is non-uniform distributed according to f, because you can tell f is a very non-uniform function. I'm going to stop now, and next time we continue with the sampling mechanisms. There is a homework that has a sampling problem in it. For this homework, you also have to